Right. So, Proposition 6 of Book 1 says it's kind of the converse of Proposition 5. So it says that if in a triangle two angles are equal to one another, then the sides which subtend those equal angles are also going to be equal. So in other words, if you have a triangle with two angles that are equal, then the sides that are being subtended by the angles, which basically means like the side that's opposite of the angle, those are also going to be equal. So assume that angle ABC is equal to angle ACB. Well, then this proposition says if that's the case, then AB is equal to AC. What's really interesting about this proposition is that this is the first time in the elements that we get a proposition or a proof by contradiction. So what do they call it in Latin? Reductio ad absurdum. So it's the first contradiction proof. So how do those start? Well, they always start by assuming that the conclusion is false. So suppose that AB is not equal to AC. All right. Well, if that's the case, then one of them is larger. Either AB is larger than AC or AC is larger than AB. And this is without loss of generality, that you can just assume one of them to be larger. We'll assume that AB is larger. So without loss of generality, assume AB is greater than AC. Well, if that's the case, we have a proposition that says from AB we can cut off a segment equal to AC. So construct DB equal to AC. And this is, which one was it? Proposition 3, I believe. So we know that they are the same, so it's not like I can use my compass to try to make some dB on here. It's basically just like choose some point on here and say, all right, there's D. And we're assuming that dB is equal to DC. And then we join, sorry, dB is equal to AC. We join DC. And again, that's postulate 1 that allows us to do that. So we'll join DC. Whoops. It's kind of joined. Yeah, that's better. Okie dokie. Well, then what do we have? If that's the case, then we know that dB equals AC. This is by construction. We know that BC equals CB. And I suppose if we wanted to add, give some kind of justification for that, I mean, it's just the same line. But maybe if we actually wanted to put some justification there, Euclid didn't, at least not in my translation. I think that's, again, common notion 4 that says that. And also, we know that angle DBC equals angle ACB. And again, this is Euclid just kind of states this fact that angle DBC equals angle ACB. I feel that there could be a little bit of justification tossed in there, because the justification is this, that angle DBC is angle ABC. Because as far as D goes, D is placed on AB. So placing D didn't somehow change this angle. DBC equals ABC, and angle ABC equals angle ACB. This is just given to us. That's given to us. So again, equals being equal to equals is, what was that again? Was that common notion 1? I can't remember anymore. After a while, we just kind of start moving away from it. It's just like, yeah, we know it. It's true. So this gives us, anyways, that angle DBC equals angle ACB. So yeah, those are true. Well, all right. So let's look at it on the diagram. We know that DB equals AC. We know that BC and CB are the same, and we know that this angle right in here, DBC, equals angle ACB. So it follows then that triangle DBC equals triangle ACB. And this is kind of maybe where things get a little bit interesting as far as this proof goes, because from this, he says this is a contradiction. He says this can't be the case. So let's see, what does he say? In quotes, I'll say, the triangle DBC will be equal to triangle ACB, the less to the greater. But this is kind of the justification right here that hopefully you go, wait, where are we getting that from? Like, where in the axioms or the propositions does this come from? Because once again, Euclid is kind of making an appeal to intuition. So basically, and the intuitive idea here is that this triangle DBC exists entirely inside of angle ABC. And yeah, based off of the diagram, that makes sense. Intuitively, that makes sense. But as far as like the formalized logic, the rigorous mathematical logic, it almost begs the question, I'd say. But, I mean, again, intuitively, it makes sense, what he's saying. It makes some sense. So he says, he follows it up with, which is absurd. It's absurd. Why would you claim that? And because of that, so the idea with proof by contradiction is, all right, we'll take the hypothesis to be true. We'll assume the conclusion to be false. We'll play around with the world where both of those are coexisting, and we'll just see what happens. And in the world where both of those coexist, we end up in a situation that logically just cannot be true. So think of this right here, triangle DBC equals triangle ACB. Think of that almost as if I was to write here that 1 equals 2. Right? It's just not true. It's patently false. So if we take the hypothesis to be true and we take the conclusion that we're aiming for to be false, and it results in some kind of logical inconsistency or logical absurdity, then we can conclude that we shouldn't have, that this conclusion cannot be false, because this conclusion being false results in something that's impossible. So, therefore, and here's how I always kind of ended proofs by contradiction whenever I was writing them. Therefore, our original supposition was false. And AB equals AC. Therefore, etc., which is what we set out to prove, right? So the first proof by contradiction, something of an appeal to intuition built in there, unfortunately, but it makes sense. It checks out. I don't think anybody would really argue too much with anything that's in the proof.